Now I will explain the practical case about heteroscedasticity and non-normality. To this end, I will use some slides which are also available in the PDF file with live Gretel screens. Consider the figures of public expenditure in health, GDP, and population in a sample of OECD countries. This data is in the OECD dataset that you can download from the virtual campus. Our goal consists in determining if public health expenditure in Spain aligns with the standards of our socio-economic environment. This analysis is often done by comparing ratios of expenditure on GDP or population. As we will see in this practical case, this is a very poor approach to solve the issue. It can be done, however, by regression methods. Tables show a comparison of ratios of public health expenditure on GDP in the case of the first table and population in the case of the second table. The results are very different. In the first case, Spain is in the 19th position with a ratio of 5.4% of GDP. The distance to the average of these countries is 0.4 percentage points, so the additional expenditure required would be around 2,000 millions, not so much. However, if we divide health expenditure by population, the position of Spain would not be very different, would be in the 21st position, but the distance to the average would increase to require an additional expenditure almost tenfold of the previous one. So we see that this approach is both not very rigorous and very unstable. An econometric criticism of previous analyses should point that, first of all, each ratio can be interpreted as a slope of a regression, with no constant term and fitted to a single data point. Imagine that you compute the ratio between this value and this value. What you are doing is computing the slope of this line, which is fitting the point perfectly. Therefore, it would be the OLS line. Second, if you compute all the ratios and then average them, the resulting average ratio would be an unbiased estimator of the slope of a regression, considering in this case all the data points, but with no constant term. So what you are doing in the ratio analysis is actually performing substandard regression. In this approach, you can only relate the endogenous variable, public expenditure or whichever, with a single variable, GDP, population, or any other. On the other hand, if you fit a regression model to all the variables in your sample, you could consider as many determinants as you want. Last, these analyses are not only simplistic but biased. You typically choose the denominator according to your interests. If you choose GDP, you would justify less difference in the public expenditure. If you choose population, you would justify an increase in spending. In this practical case, we will show that the same analysis can be done with more rigor using a regression approach. The fitted values in this case can be interpreted as the value that corresponds to the endogenous variable given the values of the regressors. If you subtract the actual expenditure to this fitted value, the resulting residual will be the deviation between the observed spending and the one that would result if the country were perfectly aligned with the standard. To reproduce the screens that you are going to see, you first need to download the file OECD GDT from the virtual campus. It has different variables about the status of the health system in the countries that we are considering. The first variable is Esperanza Vida, which is life expectancy. The second is GDP. The third is GSAN, total health expenditure, that is public and private. GSAN PUB, which is public expenditure in health. Medicals, which is number of medical doctors. The sixth is population, and there are the logs and squares of these variables. So what we are going to do is to start by modeling by least squares the relationship between the sum pub with GDP and population, which are the two variables that we are considering. If I click OK, then I see the results of the linear regression. Here you have the constant term. The slope corresponding to GDP is positive, and the slope corresponding to population is negative. This could be interpreted, for example, as a measure of economies of scale in providing public medical assistance. The R squared, as you see, is very high. If we test for normality of residuals, we will clearly reject it. The p-value, as you see, is very small. If you test for heteroscedasticity through the white test, you will see, have here the auxiliary regression, the p-value is also very small, so we are rejecting the null of homoscedasticity. So here we have a combination of non-normality or heteroscedasticity, which is a pretty standard result. If we plot the residuals against GDP, we will see that most countries are here with the dwarfs. Here is the point of the United States. Here is the point of Japan. Here is the point of Germany. So we have here a problem of giants and dwarfs. A standard solution for this problem consists in modeling the relationship between the logs of the variables that we are considering. Again, ordinary least squares, log is some pub, we discard these two variables, and then we specify the model with log GDP and log population. If we click OK, now we have slopes which can be interpreted as elasticities. This slope here means that if we are comparing two countries with the same population, a 1% more GDP in one of them would bring an increase in public expenditure in health of 1.27%. So, public expenditure in health can be considered a superior good. About population, a difference of 1% in the population of these two imaginary countries could bring down the public expenditure in health by 0.29%. The R squared remains very high. True, we know that we cannot compare this value with the previous one. If we test for normality, now we see a much better configured histogram. And the statistic is close to non-rejection, 4.7%, very close to 5%. If we test for heteroscedasticity using the white test, we see that we don't reject the null of homoscedasticity. So we are solving the problem, we already solved it, or very close to solving it. If we plot the residuals against log GDP, for example, we will see a random scatter. If we plot again the residuals against log population, we will see the same. To understand why this happens, you need to choose GSUMPUB and then control-click GDP, right button, SY scatter plot, and choose as x-axis variable GDP. You click OK, and you see a clear configuration of dwarfs, which are these guys here, and giants, United States, Japan, and so on. If you do the same with GSUMPUB and population, XY scatter plot, Now we have population in the x-axis, which is what we want. We will see more or less the same situation with the giant here and the dwarfs over here. Close the window. Now we will do the same with log gsum-pub and log GDP. Right click, XY scatter plot, and we choose log GDP for the x-axis variable. We see here a standard scattering of points. This means that the log transformation reduced the difference in the metrics of the original variables. So the small countries are not so small and the large countries' values are not so large. This is what the log transformation does. If you do the same with log gsum-pub and log population, XY scatter plot with log population in the x-axis, you will get a very similar result. And this is all, guys. Thank you so much for your attention.